Let us now use Gauss law and find out the field intensity due to infinitely long straight uniformly charged wire. Field intensity, field due to means flux due to. Flux due to infinitely long straight uniformly charged wire. Here I have drawn the diagram. You can see here this is a long infinite for infinite we will put the dotted here, infinitely charged uniform wire. And for this, let us imagine a Gaussian surface which is cylindrical in shape, having three curved surfaces, 1, 2 and the third one. Since the positive charge is lying over the line, the field direction will be always outward to the line, either in this side or in this side. For simplicity, I have drawn in only single direction, that is upward. Right? Now the three faces 1, 2, 3. If we draw the normals, the normal will be for this surface. This is outward drawn normal this direction. For this is outward drawn normal in this direction, and for this is upward direction. You can see here clearly the angle between E and N is 90 degree. Again here also E and N is 90 degree, but here the angle between E and N is 0 degree. So it means the flux for this will be 0, flux for this will be 0, but the flux for this value will not be 0. Let us do it. For the surface 1, that is phi 1, flux is given by E S cos 90 degree is equal to 0. Similarly, flux phi 2 is equal to E S cos 90 degree is equal to 0. But flux 3 at the third surface is E S cos of 0 degree, which is ES. Now using this formula, putting this in Gauss theorem, phi, total flux phi is given by integral of E ds ES, right? ES. So put E is taken outside, integral of total surface. When we put the integral here, it means we are taking the small surface. So whole integral is given by, total surface integral is given by 2 pi r L, where L is the length and r is the radius. So flux is given by E is equal to 2 pi r L is equal to Q upon epsilon naught. For linear charge density, we know that E 2 pi r L is given by, Q is given by lambda L upon epsilon naught. Since we know that lambda, which is the linear charge density, is given by lambda is equal to Q per unit surface S. So from this surface line per unit line L, so Q is equal to lambda L. So E is given by lambda L by 2 pi r L into epsilon naught. L say L cancel. So we are left with E is equal to lambda upon 2 pi r epsilon naught. It means E is inversely proportional to r. Also, if lambda is greater than 0, means if lambda is positive, the lines are directed outward, right? And if it is negative, it is directed inward. So this is the field intensity for a linear charged straight wire. We can easily prove that the direction is radially along the radius. If we consider a point here for any two points for this, let this is P1 and this is P2, right? For this, the field intensity at this point is given by E1, and for this point it is given by P2. Let me represent E2 more clearly. If I draw it here, positive charge P1 and P2 point. So at any point P, if we are going to find out, so if I join this becomes E2 and this becomes E1. So let this angle is theta. So resolving this angle, this value become E1 cos theta and this becomes E2 cos theta. Similarly, if I resolve this component vertically, this becomes E1 sin theta and this component will become E2 sin theta. So clearly this component being equal and opposite cancel out, and this gives you the net value of resultant. It means the direction of field intensity due to linear charge density is directed outward for the positive charge and is along the radius. Clear?